Next topic in Unit 4 is Thevenins and Nortons Theorem. Let us have a look at Thevenin's theorem, the statement. Thevenin's theorem states that any circuit with multiple sources, whether it is dependent or independent, and resistors can be replaced by an equivalent circuit containing a single voltage source and a single resistor in series. The purpose of Thevenin's theorem or Thevenin theorem aims at simplifying a complex network and then proceeding with the analysis. So a given network with a combination of dependent and independent sources and combination of resistors can be converted to a simple network of one equivalent voltage source in series with an equivalent resistance. So the picture shown here represents the Thevenin's equivalent circuit. Now Thevenin's theorem and Norton's theorem are always discussed together because they have almost all the factors similar except the source representation. So let us have a look at the Norton's theorem statement. Norton's theorem states that any circuit, again with sources and resistors, can be replaced by an equivalent circuit containing a single current source and a single resistor in parallel. So the highlighted words are the main difference between Thevenin's theorem and Norton's theorem. Thevenin's theorem, the equivalent circuit represents a voltage source in series with a resistance, whereas in Norton's theorem, the equivalent circuit representation is a current source parallel with a single resistor. So a Norton circuit can be represented as an equivalent current source in parallel with the equivalent resistance. So both Thevenin's theorem and Norton's theorem aim at reducing the complexity of the given network in the form of a voltage source in series or a current source in parallel with a single resistor and then continuing with the analysis technique. So the steps in the Norton's and Thevenin's analysis method are: first, we need to compute the Thevenin's equivalent voltage, which is otherwise called as the open circuit voltage, and then we need the equivalent resistance value, that is called the Thevenin's equivalent resistance. When we calculate the equivalent resistance, as we are focusing only on the resistance value, we need to make the sources present equal to 0. That is, if you have a voltage source, we can short circuit it to make its effect 0, or if you have a current source, we can open circuit that in order to make the source effect 0. So this point is quite similar to when we apply the superposition theorem. So step 1 is for calculating the Thevenin's voltage. Step 2 is calculating the Thevenin's resistance. Now if we need to calculate or represent the Norton's equivalent circuit, we may have to find out the equivalent current source value also. Once we find out these three information, the last step is the representation, that is the circuit drawing. Replace the given network with VTH in series with RTH, and in Norton's, replace the given network with IN, that is the current source, in parallel with RTH. Let us have a look at one example. So here the question is, determine Thevenin's and Norton's equivalent for the part of the circuit at A, B. So what you are asked to do here is, you are given a network with a combination of some resistors and voltage source. We need to represent an equivalent circuit for the left side of this AB, terminal AB. That means we need a representation for this part in a simplified form. This is called as the Thevenin's equivalent circuit. So in order to do this representation, we need to first calculate the value of VTH and then we need to calculate the value of RTH. One point we need to remember throughout the analysis that we are not at all touching the load resistance RL. That means there is no change for the load resistance RL. We are transforming or converting the network to the left side of the terminals A and B only. So the first step in the analysis, in order to calculate VTH and RTH, the first thing that we need to do is remove the load resistance and let us have an open circuit at the terminal A and B. So there is an open circuit at the terminal A and B and we need to calculate the voltage at this point. Now look at the network. Since A and B are open circuit, you know that there won't be any current flowing through an open circuit. That means there cannot be any current flow through the 7 ohm resistor. The network is complete through a single loop, and if you look at the voltage, that is a Thevenin's voltage, is nothing but the voltage across the 6 ohm resistor. If you want to measure or calculate VTH, we can simply calculate it by the voltage across 6 ohm resistor. Now that calculation is very simple here now because we have a single voltage source and 2 resistors now connected in series. So here what happens is a voltage division. The total voltage gets divided across the 2 resistors. Now if you want to find out the value of voltage across 6 ohm, the method will be total voltage multiplied with that resistance across which we need to find the value divided by the total resistance. So let us do the calculation. So VTH will be equal to the total voltage, that is 12 volt, multiplied with 6 ohm divided by that sum of the 2 resistors, that is 3 plus 6. So you get the answer equal to 8 volts. So 8 volts is the voltage across the 6 ohm, which is exactly the same as the voltage across the terminal A and B. We have used here the voltage division rule so that we get the answer in one step. You can do the same calculation by first finding the current through the network and then multiplying with the concerned resistor. So here we calculated our first information, that is the value of VTH. The next information we need is the value of RTH. RTH is also calculated with the same open circuit at the terminal A and B. The difference here is, since we want a resistance value, we need to take care about only the resistors. That means the source present here need to be made equal to 0. So how do we make a voltage source equal to 0? In the place of the voltage source, we need to connect a short circuit. So now look at the network. It's only series parallel combination of resistors. So what is the combination now? We want the total resistance at the terminal A and B. So if you start from the other side, you can see that 3 ohm and 6 ohm are connected in parallel, and that combination is connected in series with 7 ohm. So let us first calculate the equivalent resistance between 3 ohm and 6 ohm. So 3 parallel to 6, that gives you the resistance of this combination as 2 ohm. So now the circuit can be represented like this, where 2 ohm represents the total value of 6 and 3 connected in parallel, and that is in series with the old 7 ohm. So now You can see that 2 ohm and 7 ohm are connected in series. So the total resistance at the terminal A and B can be calculated just by adding the two values. So RTH is equal to 9 ohm. So we have calculated 8 volt, that is the equivalent voltage VTH, and RTH is equal to 9 ohm. Since these are the two information required to represent the Thevenin's equivalent circuit, now we can proceed to the last stage of drawing the equivalent circuit. So this was the original network. Now we are transforming it to the Thevenin's equivalent circuit. VTH is equal to 8 volts and RTH is equal to 9 ohm. So Thevenin's equivalent circuit is completed. Since the same question you are asked to get the Norton's equivalent circuit also, if you remember, Norton's equivalent circuit has a single current source in parallel with a single resistor. The value of the resistor is same whatever you have found for the Thevenin's equivalent circuit. Now to find the value of the current source, we can just do a source transformation. You remember the previous topic, source transformation. A voltage source in series with the resistor can be converted to the equivalent current source in parallel with the same resistor. In order to find out the value of this current source, we just need to do Ohm's law. I is equal to V over R. V is the 8 volts and R is 9 ohms. That gives you the current value equal to 0.89 ampere. So that gives the Norton's equivalent circuit representation. So have a look at the original circuit given. You have multiple resistors connected in series and parallel, and there could be multiple sources also, whether it is a voltage source or current sources. The whole information need to be transformed into a symbol representation of a voltage source, single voltage source in series with a resistor, or a single current source in parallel with a resistor. This transformation or this representation is called as Thevenin's equivalent representation and Norton's equivalent circuit. So always the final step in this type of problem will be the equivalent circuit representation, either as Thevenin circuit or as Norton circuit. The steps to calculate the value of this VTH, RTH may vary depending on the parameters, connection, their values, and the overall circuit. But the final answer, the final step representation will be always the same.